All right, so second day of this section 4.3, we're doing a little more increasing, decreasing stuff, and then the big bulk of today is going to be on this first derivative test, which is very, very important. So first we're going to do one more example of an increasing, decreasing problem. So where is this function increasing? Where is it decreasing? So again, we're looking for the derivative. So this is going to be based on where the derivative is positive and where the derivative is negative. So of course, if we want to find the sign of the derivative, we first have to find what the derivative is. So let's start there. So f prime of x equals the derivative of x cubed is 3x squared, and then the derivative of 4x is 4. Okay, so this right here, again, just like we did in the sign chart on the previous page, in the previous set of notes, we first set the derivative equal to 0 so that we can set up a sign chart, because those are going to kind of be our splitting points. If we find we're at 0, then we can break up the number line into different intervals and find where the derivative is positive and where the derivative is negative. So this is going to be maybe kind of an unfortunate, irrational sort of thing here. So x squared equals 4/3. So that means that x equals plus or minus 2 over root 3. Not the prettiest of values, but we can use that to set up a little sign chart. So again, this is going to represent the sign of f prime. So here's negative root 2 over 3, and then here's positive root 2 over 3. So what this does is it splits our f prime sign chart, our number line, into 3 different values. So we're trying to see where f prime is negative and where f prime is positive. This splits this up because we know here that it's 0. Okay? So if I plug in something to the left, now let's just go with something safe. You don't really need to know what negative root 2 over 3 is to figure out something smaller. Like negative 100, for example, is definitely smaller. So if I plug negative 100 into my derivative here, I get 3 times 100 squared, and then minus 4. That is definitely going to come out to be positive. So anything in here that I plug in, I'll get a positive value. I know I get 0 when I plug this in. Now let's plug in something in the middle. Again, a safe value would be 0. We know that 0 is definitely in between these two values. So when I plug this in, I get 0 minus 4. So that leads me to believe anything in here would be negative. I know that this is 0. And then when I plug in something bigger, again, I can use 10, I can use 100, I can use 1,000. When I plug 100 into this formula right here, I'm definitely going to get something positive. All right, so that's my sign chart. Tells me what I get if I plug different x values into the derivative, and that will help me find when my function is increasing and when it is decreasing. So I say that f is increasing on, and then I write my intervals. So from negative infinity to negative root 2 over 2, and then I write the little union symbol because I have a second one to join on here, positive root 2 over 3 to infinity, because, remember I always have an answer, because f prime is greater than 0, and we can just say like there or on those intervals or something like that if we don't want to rewrite the whole interval. And then f is decreasing on, and then we choose that interval in the middle. Because f prime is negative there. There we go. So that would be our answer. We got our intervals. We've got our AP explanations because the AP test would make you write explanations like that. So we will practice them now. So here's a little corollary. This is a little bit strange. But so if we know that f prime is equal to 0 everywhere, so we know that the derivative is always 0. That means like a constant horizontal line for the derivative. The derivative is only equal to 0 if, like I said, my function is a horizontal line. So then that must mean that f prime of x is equal to c on that interval I for some constant c. So the only way to have a derivative that's always 0 is to have a function that's always constant. All right, so that's what that means. If we know the derivative is 0, the function must have been some sort of constant, a horizontal line. Okay, so now we move on to our big stuff for today. The first derivative test for relative extrema. Okay, so now one thing I want to point out. Relative extrema, local extrema, same thing. Okay, so relative, aka local. This is one of those things, if you remember with like sine and cosine inverse, We could see sine inverse or we could see arc sine. You never know what the AP test is going to give you. They might say local, they might say relative, so I just want us to know that those are the exact same thing. So relative or local, same thing. So a function f may have relative extrema at some critical points while failing to have relative extrema at others. Let's look at a handful of possibilities. So we've got all sorts of things happening here. So I want to walk you through every single one of these values from a to all the little constants up until b. All right, so here, a is an absolute min. We learned in one of our sections that absolute min can happen at endpoints, and that appears to be what happens here. The next one. So now all throughout here, my derivative is greater than 0. My function is increasing. And then what happens right here is I have a critical point because my derivative was 0. But then after that point, my function continued to increase. And so this turned out not to be an extreme value because my function was increasing, stopped for a moment, and then it continued increasing. So it's not a max, nor is it a min. Move to this point at C1. Here I've got another critical point because my derivative is equal to 0. To the left, my derivative is positive, which means my function is increasing. To the right, my derivative was negative, which means my function was decreasing. And so this turned out to be a local max. So my derivative went to positive to negative, which means my function was increasing, then decreasing, and that turned out to be a local max. Not the absolute max, because there are other values around it that are bigger, but it's the biggest one in its general vicinity, which is what makes it a local max or a relative max. Okay, so we know that my function's decreasing, which means it has a negative derivative. And then here's another point that counts as a critical point because my derivative is 0. So my function has a negative derivative, then a positive derivative with this derivative of 0 in the middle, which means my function's decreasing, then increasing. Well, this turned out to be a local min for that very reason, or a relative min, because my function switched from decreasing to increasing, or in other words, my derivative changed from negative to positive. Up here, that's a critical point, but it's because f prime is undefined. This is a non-differentiable point, so that's a point that's undefined, but still I can see that my derivative switched from positive to negative, which means my function switched from increasing to decreasing. This, not only was it a relative max, it actually counted as the absolute max when we went and plugged everything in. It's the very biggest point, but again, it also counts as a local max or a relative max. Here, I have another critical point. My derivative is equal to 0. My derivative changed from negative to 0, but then negative again. So since I had no change in sign, my function was decreasing, it stopped, and then it continued decreasing. So this is not a relative max, nor is it a relative min. And then down here, this is the lowest value that I'm going to have in a while, and so that's a local min. It happened at an endpoint. Okay, so hopefully that makes sense. We've got lots and lots of different possibilities there, and so everything that we're doing here, we can write down in this theorem. We have a couple options here, multiple options really. So this is happening, first of all, C. This is happening at a critical point, C. That's what I'm talking about when I'm talking about C. So if f prime, the derivative, changes sign from positive to negative, then, so now let's look here. Positive derivative, negative derivative. Okay, so this is the example I'm talking about. My derivative changes sign from positive to negative. That ended up being a local max. So let's write this down. So if my derivative changes from positive to negative, then f has a local maximum at C. Or relative, that works too. So 2 pictures, in case you're wondering what all this space is for. Picture number 1 could be your nice, kind of run-of-the-mill parabola, something like that. So here at C, my function has a positive derivative, then a negative derivative. So over here, positive derivative, over here, negative derivative. Right there is a derivative of 0, and that ended up being my maximum. I could also have one of those situations, not where the derivative is 0, but where the derivative is undefined. And so it could look something like this. Okay, so again, right here, that's C. Over on the left, I have a positive derivative. Over here on the right, I have a negative derivative. Here, my derivative is undefined. It does not exist. Here, I forgot to write this down. My derivative was 0. So two different ways to have a local max. All right. Next, if f prime changes sign from negative to positive, that's what I'm dealing with here. Negative derivative, positive derivative, that means I've got a local min. Okay, so that's what I'm going to write down. So then f has a local or relative. Again, we're going to try to use those interchangeably. Okay, so two different situations here, just like I had. So say I've got, same thing, just kind of your run-of-the-mill parabola. So here at C, right here, my derivative is equal to 0. Over here, my derivative is positive. Over here, my derivative is negative. That gives me a local min. Let's say that I had something like this. That point's undefined because it comes to a nice sharp corner here. But if I look, this derivative is still negative on the left. This derivative is positive on the right. This one just happened to have a derivative that does not exist or was undefined. So remember, there are two different ways to have critical points. Critical point could be a derivative that's 0 or a derivative that's undefined, which means if I'm looking at a picture, there are two different ways to have relative mins. Okay, one more thing. And this is what happens here and here. That's the last option, is that you don't end up having an extreme value. So last thing to write down, if f prime does not change sign, so either it's 0 or it's undefined, but it doesn't actually change sign, then f has no local extreme. So let's say neither a max nor a min. At x equals c. So neither a max nor a min at x equals c. So one of two things could happen here. Really, actually, one of four things could happen, but I'm really only going to draw two pictures. So we could have like a nice little cubic function, kind of levels off, but then it continues increasing. So this would be your point c, right at the origin here. So here my derivative is positive. It slopes off for just a moment right here, but then it continues to be positive. So there's no sign change. My derivative didn't change signs at that point. So that means it's neither a max nor a min. It just happens to be a point where my graph levels off for a moment. Or let's look at a critical point that has an undefined derivative. So say it's doing something like this, and then it goes like that. So it's kind of rounds down, stops at this point. So at this point, my derivative is undefined, but I go from having a negative derivative to an undefined derivative, and then again to a negative derivative. So that is neither a max nor is it a min. Just because my derivative is 0 does not automatically give me a max or min. I have to have a sign change. All right, so let's read that little blurb I've got here. Critical points. What happens is they partition the x-axis into intervals on which f prime is either positive or negative. That's why we make the sign charts. So we can determine the sign on each interval by just plugging in a test value. So first derivative test, we are going to find relative extreme values. And then we also want to identify any absolute extrema. And so we'll recap what we did on that in the last section as well. So here's my function. I've got x cubed minus 12x minus 5. So I start by finding critical points. And then remember, the critical points partition my x-axis into different intervals. So critical points are where the derivative is equal to 0, which is how I was doing that in the previous section that we watched yesterday. So start with the derivative. Derivative of x cubed is 3x squared. And then minus the derivative of 12x is 12. The derivative of 5 is 0. So I want to set this equal to 0, but before I set it equal to 0, I'm going to factor it down because that's going to really help me out. So here I can factor out a 3, and that leaves me with x squared minus 4. And then the x squared minus 4, we hopefully recognize that that factors down to x plus 2 and x minus 2. Okay, so now we want to set it equal to 0 so we can find our critical points. As a reminder, critical points happen when my derivative not only is 0, but it could also happen when my derivative is undefined. So always keep an eye out for derivatives that are undefined. It's not going to happen here because I have a polynomial, but I am going to find 2 points where my derivative is equal to 0. So my critical points, we've got x equals plus or minus 2. Okay, so we're going to get in the habit now of labeling our critical points. It's a really good habit to be in. So critical points happen at plus or minus 2. And so just like we set up here, The critical points partition the x-axis into intervals. And on those intervals, my derivative is either all positive or all negative. So I'm going to do a sign chart that represents the sign of f prime. And so I partition at -2, I partition at +2. Keep in mind that those numbers have to be in numerical order, otherwise it'll totally mess you up. So I know for sure that my derivatives are 0 here and here. So what this says, I can evaluate f prime for just one value on each interval. Just pick any test value. So if I test something right here, -3, or I could go more extreme and do like a -10. If I plug in a -10 right here, then I have 300 minus 12. The larger we make our numbers, the more obvious it makes it if it's positive or negative. So here I get something positive in that whole interval. Here, the best choice is 0. The best choice is always 0 if it's available to you. So if I plug in 0, 0 squared minus 12 is definitely something that is negative. So my derivative will be negative on that entire interval. And then after 2, again, plug in something like 100. Plug in something as big as you want. Make it very obvious what sign this thing is. If I plug in something like 100, this thing minus 12, definitely going to be positive. Okay, so that's my sign chart. I've got 3 different intervals. I found what sign my derivative is. So I know that my function is increasing here, then it switches to decreasing, and then it switches to increasing. So if we figure out exactly what the max and mins are going to do, we can see if we're looking at the sign of f prime on each interval, we're going to find some local maxes and local mins. So let me draw a couple things on here. So my derivative is positive, which means my function's increasing, then it switches to decreasing. So when I switch from increasing to decreasing, this right here would be a local max. Okay, then what happens is I'm decreasing, and then I switch to increasing. When I switch from decreasing to increasing, that is a local min. So again, my derivative changes from positive to negative, I get a max. If my derivative changes from negative to positive, I get a min. And that's because this change from positive to negative means my function is increasing, then decreasing. And this change means my function's decreasing, then increasing. All right, so let's actually write everything out. And then let's talk about what sort of explanations you would write. So for your AP explanations, which I want you guys to start practicing right away, you would say that f has a relative max or a local max, whichever one you're more comfortable with, at x equals -2, because f prime switches from positive to negative. We can do some abbreviating right now, but we don't want to do too much abbreviating in the AP test. So that's one thing we know. Next thing we know, f has a relative min at x equals 2 because f prime switches from negative to positive there. Okay, and again, probably don't want to do the abbreviating on the actual AP test. And then last thing, it says identify any absolute extrema. So this, my function is increasing, then it decreases for a little while, and then it increases. So just to give you that general shape, it's going to look something like this. Just a very rough sketch. So you can see the relative min, the relative max. However, because I've got this open-ended interval, I'm not ever going to have an absolute min or an absolute max because I'm not looking on a closed interval, I'm looking on a big open interval. So what we could say is no absolute extrema. No absolute max, no absolute min, since I go all the way from negative infinity to positive infinity. So my function, those y values, they're going all the way from negative infinity to positive infinity. I'm not going to have a largest value or a smallest value. Okay, another one of these. Here's my function g of x. First, I start by finding critical points, and the critical points are where my derivative is 0 or undefined. So of course I have to find the derivative first. This is going to require a nice little product rule. So my first function, u, that's x squared minus 3. My second function, v, is e to the x. So uv prime v prime is just e to the x, and that's because e to the x is the best derivative ever. And then plus v u prime. So u prime is going to be a 2x, and then, of course, e to the x. So what I'm going to do is I'm going to factor out this e to the x and then write the leftover stuff in parentheses. I'm going to put it in standard form, which means x squared, then the 2x, then the minus 3. So that's my derivative. I want to find out either where the derivative is undefined or where the derivative is equal to 0. This derivative is never going to be undefined. I can plug anything I want into this exponential function. I can plug anything I want into this polynomial function. So I'm just looking for what's equal to 0. So what I'm going to do is, first I'm going to leave e to the x just the way it is. I'm going to factor this down. And this factors down to x plus 3, x minus 1. So I can basically set them all equal to 0 and see what I get. So if I set e to the x equal to 0, I don't actually get anything because e to the x will never be 0. So that gives me nothing. But I get negative 3 and I get positive 1. And remember, we're going to label those. Those are my critical points. Okay, so 2 critical points to work with. Remember what we did up above is my critical points break the sign of f prime into different intervals. They partition the x-axis into different intervals. Have to put them in numerical order, otherwise the partitioning won't work. And so I pick different values to plug them into this function right here. Here's a little note that I would like to make. This is something that's very important when I am looking at my interval. This guy right here, the e to the x. E to the x is always, e to the x is always, that'd be an easy word to spell, here we go, always positive. So e to the x is always positive no matter what you plug in. It's an exponential function. So you can almost kind of ignore it when you're working on the sign of everything else. So say I plug in like negative 10. Negative 10 plus 3 is negative. Negative 10 minus 1 is negative. So I have a positive times a negative, and that is going to come out positive. Okay, then plug in something in here. Plug in 0, super easy. E to the 0, again, positive, because this is always positive. 0 plus 3 is positive. 0 minus 1 is negative. So positive, positive, negative. That gives me a negative for my middle section here. And then something bigger than 1. I could use 2, I could use 1,000, I can use whatever I want. This term right here is always positive. X plus 3 would be positive, and x minus 1 would be positive. And so this last one ends up being positive. Okay, so answer the same questions. So I've got these 3 different sign areas. I'm going to figure out what values are maxes and what values are mins. So same logic as we just had with part A. So negative 3. So f has a relative max at x equals negative 3. Reason being, same reason as up above, because f prime switches from positive to negative there, which means my graph goes from increasing to decreasing. Okay, and then right here at 1, my graph switches from negative to positive, which means it's decreasing then increasing. That would be a relative min. Okay, last thing is they ask about the extreme values. This has the same, it's got the same increasing, decreasing, increasing pattern, but actually the left end behavior is really, really different than this function. So I want to show you this value here. All right, so let me show you what the function looks like. Okay, so we have in parentheses x squared minus 3 and then times e to the x. Okay, so our graph looks like this. Again, it still has that increasing, decreasing, increasing pattern, but like I said, this left end behavior is quite different. So when we're talking about absolute mins and maxes, we don't have an absolute max because it goes on forever over here. We do actually have an absolute min though. The absolute minimum value is going to be whatever g of 1 is, and that's this value as we come over here. All right, so an absolute min. The graph is bounded below by 0. Okay, so it is bounded below. So that means that whatever I get at this value right here, g of 1, that's going to be the local min. Because I don't ever go lower than this. I'm bounded below by 0. So whatever this value is also a min, which is going to be this one right here. Okay, so this point right here is also what we can call the global min, which is the same thing as the absolute mins. That's another vocab word to throw at you. Global and absolute are the same as local and relative are the same. All right, so last one here. H of x, and then suppose f prime equals h of x. We want to plot h of x and then use the plot to describe the local extrema. So we're just going to do that on a calculator. Okay, so new calculator. New graph. So we're going to plot this function x and then times x squared minus 1 over x squared plus 1. Why not? Let's try multiplication there. There we go. Okay, so our graph looks something like that. So let's graph a quick sketch. So it almost looks like it's linear, and then in between we do this weird little like come up, come down sort of thing. So let's graph that. So this is a quick little sketch. So it's coming in like this, almost like it's linear. Dips up, goes right through the origin, dips down, and then comes up and does that same thing, like almost a linear pattern. So this is h of x, which, remember, we are pretending that that is the same as f prime. All right, so if we know that this is f prime, we're going to use that behavior to describe local extrema and then describe the increasing, decreasing behavior of f of x. So, again, we are pretending that this is f prime. So when we're talking about increasing, decreasing behavior, we want to know when is x prime positive, when is x prime negative. All right, so of course here, f prime is negative, f prime is positive, f prime is negative, and then f prime is positive. These values right here, if we look back at our graph, that's actually, whoops, come on. This is -1, 0, and +1. Perfect little intercepts there. So this is -1. This right here is a +1. Should probably put that in black just so we don't mix those lines up. So -1 and +1, and then of course right through the origin. So here, my derivative is negative, then my derivative switches to being positive, which means that I have a relative min at x equals -1. And again, this represents the derivative. So my derivative changes from negative to positive. That means my original function is decreasing, then increasing. So I have a relative min at -1. Same thing happens here at +1. Okay, and then at the origin, I have a relative max, and that's because my derivative goes from positive to negative there. Okay, so I've got the local extrema, covered that, and then the increasing, decreasing behavior. The graph is increasing. We want to know when f is increasing. F is increasing whenever f prime is positive. So that happens from -1 to 0, and then from 1 on over to infinity. And then we are decreasing. F will be decreasing whenever f prime is negative. So that happens from -infinity to -1, and then again from 0 to 1. All right, so a couple different pieces there. And now, again, we want to sketch a plausible graph for f itself. So let's take a look. So we got to put all this stuff together. So at -1 and +1, we're supposed to have relative mins. And then at 0, we're supposed to have a relative max. We're supposed to increase on this interval, and then increase on this interval, and then decrease here and then here. So my function is going to, I'm just going to kind of make this up. So my function is going to decrease until I hit -1, and then I'm going to have a relative min. And then my function is going to increase from -1 to 0, where I'm going to have a local max. And then my function is going to decrease from 0 to 1, and then at 1 I'll have a local min. And then afterwards it is going to increase. So something like that. That is just a plausible graph for f. So you can match all these values here. And here my derivative is negative, and that's where my function decreases. Here my derivative is positive, that's where my function increases. And then again, negative, positive, decreasing, increasing. So this is a plausible graph for f of x. Just a sample one though. Okay, sorry that went a little long, but that is it.